In this chapter, we will be looking at subatomic particles and exploring how radioactive decay changes the nucleus. Developing an accurate model of the atom was an ongoing process, and an understanding of radioactivity led scientists to discover more about the internal structure of the atom. You should recall from Chapter 6, from studying chemistry, that Thomson's discovery of the electron led to further investigation of the internal structure of the atom. Thomson, his model was that of a raisin bun, so he thought that the atom was essentially a positive mass and the electrons were scattered throughout. Ernest Rutherford used radioactivity as a means to study the atom. What he did was he directed a stream of positively charged particles at a sheet of gold foil, a really thin sheet of gold foil. And instead of passing through the gold foil, as was expected according to the Thomson model, some particles were deflected back and some bounced straight back. So some particles were deflected back and some bounced straight back. Most of the particles went straight through, but it was expected that if any were to get deflected, they would only be deflected a little bit, and that some came straight back was really shocking. So what they concluded was that an atom is mostly empty space, and all of the positive charge and all of the mass is in the nucleus. So most of an atom is empty space, because most of the particles went straight through, and all the positive charge and mass is in the center, and this is called the nucleus. He then came up with the idea that electrons surrounded the nucleus. So he knew that the electrons weren't in the nucleus, they surrounded the nucleus, and he then developed what is called the planetary model of the atom. And this model had some problems, and Niels Bohr was the one who suggested that electrons, they exist in specific orbitals, and he came up with the Bohr model. We're now going to revisit the subatomic particles, protons, neutrons, and we're also going to look at isotopes. So you should recall that protons are in the nucleus and neutrons are in the nucleus, and protons have equal but opposite charge to an electron. Oops. So protons have equal but opposite charge to an electron. And compared to an electron, they are huge. They have a mass that is 1,800 times greater than an electron. Neutrons have no charge, that is, they're neutral, and they have a similar mass to protons, 1,800 times greater than an electron. The atomic number for an atom is the number of protons. That's what defines it as an element. And the mass number is the number of protons plus the number of neutrons. since it is the protons and the neutrons that make up all of the mass of an atom. Now we're going to look at isotopes. And isotopes are atoms of the same element that have different mass numbers. And they can do this because they have different numbers of protons. Or not protons, neutrons. So they have same number of protons, different number of neutrons. Isotopes of the same element share almost identical chemical properties. And that is because isotopes have the same number of electrons, and we know that it is the electrons that are responsible for the chemical properties. But because they have different numbers of neutrons, they may have very different physical properties. So may have different physical properties. Looking at some examples of isotopes, first example I'm going to choose is carbon. Carbon has 3 isotopes, carbon-12, carbon-13, and carbon-14. So this is the mass number that comes afterwards. So that's the total number of protons and neutrons. And we know that the protons are always the same. So if we look up carbon on the periodic table, carbon has 6 protons. So carbon-12 would have 6 protons, and then 12 minus 6, it would have 6 neutrons. This happens to be the most common and the most stable form of carbon. Carbon-13 has to have 6 protons because it's carbon, but its mass is 13. So that means it's gained an extra neutron, so it has 7 neutrons. Last one, carbon-14 again has to have 6 protons, mass of 18, 14 minus 6, 8 neutrons. Another example I'd like to look at is hydrogen. Hydrogen also has 3 isotopes, hydrogen 1, 2, and 3. Hydrogen 1 has 1 proton and 0 neutrons. And this is the most common form, and we just call this hydrogen. Hydrogen 2 is 1 proton and 1 neutron. And this has a special name that you need to know, and it's deuterium. Hydrogen 3, 1 proton, 2 neutrons. And this is tritium. You're going to need to remember these names. We're going to come back to them. When an isotope is radioactive, this means that it can break apart into smaller pieces, and that's what we're going to be looking at in this chapter. And as they break apart, they also give us energy. What I'd like you to do, and I don't have it here on this sheet, but on yours, there's some isotope practice. So do the isotope practice. Filling in the tables. We will begin next class by looking at those and continuing on.